So the way that you do this problem is you first figure out the total impedance, and so you know the resistance is 15, so that's the real part. The inductive reactance is 26 ohms. So when they give you the inductance already in ohms, you know that what they're giving you, and then they say the reactance, they're giving you this part without the J. So you could say that the impedance of the inductor was J26, or you could say the reactance is 26. So those all mean the same thing. So then that gets the impedance. Once you have the impedance, you can figure out what that is in polar. You can just use your calculator to do that, and you get an angle of 60 degrees. So what that tells you is that the angle of the voltage minus the angle of the current is 60 degrees. So if I make the voltage 0, then negative the angle of the current equals 60 degrees, or the current equals negative 60 degrees. And then that works out, and then I wanted to check that, and I was hoping that would be the case, because what goes together, so this is something else that goes together. So if you have an inductive circuit, then this number is going to be positive, but your current is going to be lagging, and so its angle needs to be less than the voltage. And so that's the other reason why. And then once we have the, let's see, we didn't actually need that angle to find the voltage, because we set the angle of the voltage to be 0, and we did the current relative to that. And so we had the angle of the voltage is 0, so we just needed the magnitude, which would be the magnitude of the impedance, which is 30, times the magnitude of the current, which is 5, which would give us 150. So that would be our voltage. So any other questions? All right. Let's see, is this any different? Yeah, because we've got the first part is all the same. So the first part, there's nothing new here, but then we have part D that we're going to add a capacitor. Okay, so so we want to get the voltages across the components. Okay, so let's see, I've got a voltage source that's 100 RMS, and it's 60 hertz, and so our power supply, I believe that's 377. So omega is 377. By the way, this is standard AC. So our impedance is our resistance plus J times our reactance. So that's going to be J times, it's an inductor, so it's omega L. So it'll be 10 plus J times 377 times 0.046, which is 10 plus J 17.34, which is the same as 20.02 angle 60.03. So that is our impedance. So the phase angle of our circuit is 60.03. Our current is 100 divided by 20 angle 60.03, which is 5 angle negative 60.03. Let me check and see if I have everything the same so far. Yep. Okay, so now the voltages across the components. So the voltage across the resistor is 5 angle negative 60.03 times 10, or 50 angle negative 60.03. And our voltage across the inductor, 5 angle negative 60.03 times 17.34 angle 90, because J is just angle 90. And that gets me 86.7 angle negative 29.97 volts. The different powers consumed by the series RL circuit. Okay, so let's just do, since we have everything, let's just use these easy ones. So I squared R and I squared X for P and Q. So our real average power is 5 squared times 10, or 250 watts. And our reactive power is 5 squared times 17.34, which is 433.5 VAR. And so our complex power is 250 plus J 433.5 VA, or if I change that to polar, I get 500 angle 60 VA, Or if I just want so this is the complex power. If I want the apparent power, I'd say 500 VA. Okay, so then our problem says, okay, well look, my apparent power is 500, but my real power is 250. That's not so great. My power factor is 0.5. Did we find the power factor? We didn't find the power factor. So the power factor is P over S, which is 250 over 500, which is 0.5. And so that is not a very good power factor. So to improve that power factor from 0.5 to 0.95, what would we need to do? So what we would need to do is this. Can't move it up there. Okay, it's fine. All right, so we know what the current Q is. The current Q is 433.5. If we get the new power factor of 0.95, then in that case, Q will be 250, because our real power won't change, times the tangent of the inverse cosine of 0.95. So inverse cosine of 0.95, and then is 18.19, and then I'll take the tangent of that, and then I'll multiply that times 250. And that gets me that Q, I'd rather have a Q of 82 VAR. So then the capacitor that I need is going to be 433.5, which was my old Q, minus my new Q, which is 82, over omega, which was 377, times V RMS squared, which was 100, right? So 433.5 minus 82 over 377 times 100 squared, and I get a capacitor of 0.00009326, or 93 microfarads. Except my answer says it's supposed to be 9.3. I think I'm right. Did any of y'all do it? Okay. Yeah, I think that's right. All right, and my power is about to die, and it's almost 4:30, and that's generally when I stop on Thursday, so I think I will stop here, but I will answer any final questions. I feel like, to me, and maybe this is not encouraging because I'm supposed to know what I'm doing. I feel like finally, after doing this like a number of semesters, this is all making sense to me now. And so I'm hoping that it's making sense to y'all, that I'm conveying some of that. Is it kind of coming together a little bit?
I'll get more on.
No, I'm about to stop the recording. Let me stop it. Okay, so the last part now, we know that Q is 82 because that's what we got from doing this. So this is the reactive power. The real power doesn't change. That's still 250 watts. And so the apparent power is going to be the hypotenuse of that triangle. It's 82 squared plus 250 squared, which is 263 volt amps. And so that's our apparent power. So we brought it down from 500 to 263.